floor to Sylvain for the first part.
Thank you very much. Okay, so thank you very much for the introduction, and thank to all of you for showing up after what I believe was a rather short night. I promised to people I saw yesterday that I will make it light. This is a rather light presentation, easy topic. And I will start by telling you a bit about my trip. So that's an aerial view of our university with Lucrezia. And that's the trip I did yesterday to go to Benevento. Wow. And and I don't know about you, but when I go to a place that I don't know, it's the first time I've been here, I ask myself some questions. For instance, I went to this aerial view and I asked myself, what is that? Does look like a monument? What is this monument? And okay, you all know it's very close to here. I don't need to try to pronounce it very badly. Then I can ask myself a bit more complicated questions. For instance, how many buildings can I see in this image? This is a bit more complicated, and I would like something that could give me an answer. For instance, 103. Of course, here you might say I could count the building manually, but if I do that, good luck. You don't want to do that manually. And then I was here for a very, very short time, so I wanted to take a walk. And for instance, I could ask myself, I would like a nice itinerary for a walk that goes through the main monuments and highlight points of Benevento. So for instance, I could want a system to suggest me something like this. And if I want to go one step further, and let's say that I really love Benevento, and because I'm very rich, I'm not, I would like to buy a secondary house in Benevento. And I don't like modern flats. I want something that I'm quite sure will not move too much. So I could ask, for instance, when I want to buy a flat, which area is quite stable? For instance, in which area there was the least new building built in the last 10 years? This starts to be a bit harder questions. And for instance, I would want a system to answer me this area, which I believe would be quite correct. Okay. You might have completely different questions, but what I think is that even if they are not the same question, you are all interested about your environment. I hope so, considering that you probably all work in Earth observation. But I think also your relatives, everybody is interested in environment, either because you care about it or because you absolutely don't care, but you want to enjoy your trip to the other end of the world, polluting a lot, taking the plane. And if you had to answer the questions that I asked earlier today, I would like that you reflect a bit on what would you use. So for instance, the first one, the monument, that's very easy to do today. I guess you all agree, you go to Google Maps, you click the monument, you have the name of the monument. So that's very easy. The itinerary going through the main monuments, it's also probably something that you could do, for instance, with Google Maps, taking the main monuments and then having a script that try to find, like that call Google Maps to find the shortest path going through all of these monuments. Now, how many buildings are in the picture? This starts to be a bit more complicated. For instance, either you have a GIS approach and you would try to find a shapefile of all of the buildings, try to load it in QGIS, for instance, and have a small script that will count the building, or you are more of a machine learning guy, and you will develop a semantic segmentation algorithm to segment the buildings and count the buildings. Still doable. Now this one, it starts to really, really be complicated. So you would first need to load a time series of high-resolution images. That's, in general, hard to find and quite expensive. Segment the building, do change detection. I'm pretty sure that unless you really want to buy the flat and you want to invest wisely, you will not do that. Okay, so again, everybody is interested in their environment, but even if you follow the IADF school and you are an expert in Earth observation, it's hard to answer this type of questions easily. It would take some time. And that's for you in this room. But what about your parents, your brothers and sisters? They probably don't know that QGIS even exists. They cannot do this type of tasks. So that's why we launch this visual question answering for remote sensing task as VQA. This is a nice demo made by Lucrezia that explains a bit how it works. But basically, we would like to have a system that takes an image and a question as an input, the question being in natural language, in English, and will provide an answer in English as well. So for instance, what is the amount of roads on the left of the park? And the system would answer too. This idea comes from this paper that was published in 2014 that is by Jeman and Jeman. Maybe some of you know it? Like, no? Okay. That's for older people, maybe. So they are the people who made it possible to use Markov random fields in image processing. So they made a lot of contributions to the field of image processing. And basically, they define this task as a visual Turing test. You all know the Turing test, right? Maybe you saw the imitation game about Alan Turing. And actually, yeah, so then the idea was put in practice by this paper, for which we'll celebrate the 10-year anniversary in 2 months. I found out that when I did the slide. But basically, yes, so in computer vision, general computer vision, they started this task of visual question answering. Basically, the point was to take natural images, ask questions, try to get an answer. So you have some examples. So for instance, what color are her eyes? What is a mustache made of for the top left picture? And in this paper, they took 200,000 images from MS COCO, that is a widely used dataset in computer vision, and they used Amazon Mechanical Turk, I will come back on that, to collect a lot of questions and answers from real people, and then they trained some models to try to answer automatically these questions. So that was 10 years ago. Again, like I just want to remind people that, do you remember when ChatGPT was introduced? Like November 22, yeah? So that's 3 years ago. So 10 years ago, this seemed completely crazy to try to talk with images. I know that today it seems a bit more normal, but back then it was a bit crazy. And of course, when you see these examples, you could think, what's the point? Like, why do we know what is a mustache made of? So maybe it's indeed something that we can do with our phones today. You tried this kind of thing, but one really nice application that was proposed in computer vision almost straight after this paper that I've just shown you is to help visually impaired people. So, for instance, with this type of images. So you could imagine visually impaired people working with a camera and being able to ask about their environment. For instance, they turn the thermostat on their oven and they want to know at which temperature is it, or is it still on? This kind of task. So I think this was a nice application that was really useful. And indeed, as you said, I was in the Netherlands, in Wageningen, for my postdoc. And at the start of my postdoc, we tried to find what I would be working on. And we had this idea that indeed people are interested in their environment, but accessing information about your environment is hard. So we started working on visual question answering for remote sensing in 2017. As you might be able to see here, okay, here, the paper was published in December 2020. It took me 3 years to finish this paper, which is an absolute record for me. But it led to a lot of exciting projects from my lab and other labs, and I will tell you a bit about not all of these projects, but a good chunk of them. So first I will start with the basic paper here, and then in a second part we will look a bit at what has been done since 2020 on the topic. To talk about this paper, I will divide it in 2 parts. First, I will talk a bit about the data, which of course is important. As you might have guessed, we'll use a lot of deep learning to try to solve these tasks. And in a second part, I will talk about the models. So let's start with the data. Of course, we need data always to evaluate models, right? You all know that. But also, if we want to do supervised machine learning algorithms, we need this data to train our model. So that was the first problematic that we had. We needed to build the data sets to be with samples that are image, question, and answers triplets. So for instance, you have a sample here. I took again an image of Benevento. Is there a park in this image? Yes. You could consider that this is a park. So we want to build triplets like that. And back then, there was no data set that had this kind of triplets for remote sensing. And so we looked a bit at what were our options. So the first option was to do like the VQA paper. I don't know if you remember, I talked about the fact that they used Amazon Mechanical Turk. Who know about Amazon Mechanical Turk? Yeah? Great. So basically, it's a platform provided by Amazon. That is a bit a weird platform. You can give very, very simple tasks that Amazon will distribute to workers, human workers, all around the world. And for about 10 cents, at least back then, they will solve your task. So the task can be to solve a CAPTCHA, for instance, or to ask a simple question about an image, or to answer this question. So that's what they did in this paper. They took all of the images from MS Coco, they sent it to a lot of different workers, and they asked people to ask questions about the images, and once they had the questions, they asked people to answer the questions. So that's super nice because it's representative of what the user will really ask, since it's real users who asked the questions. But the problem is that it's very costly. So we computed that it was about $100,000 to get 80,000 questions answered per. And it's hard to extend. I mean, if instead of 80,000 question answer pairs you want 160, you need to pay $200,000. So I went to see my supervisor, Davis Tuya at Wageningen, and I asked him, do we have $100,000 laying around somewhere that I could use for my project, we have no idea if it's going to work? And he told me that's what I cost for about a year, so it was either I get a salary or we do that. And since I like being paid, we try to think of another option. The second option was to use OpenStreetMap data. So I guess you all know OpenStreetMap. It's kind of a free equivalent to Google Maps that is filled by voluntary people. So you can all go and check that the place you live in, for instance, is well referenced in OpenStreetMap, the building is well delineated, and all of that. And so we thought, okay, if we can use this OpenStreetMap data to automatically build these image question answer triplets, sure, it would be a bit less representative of users' need because we would automatically build it. So that's always a bit less nice. But at the same time, it would be still a bit manual because it has the data set of OpenStreetMap has been done manually. And it would be completely free and easy to extend. If we find out that 80,000 samples is not enough, we can extend and do much more for free. So of course, that's the option that we chose. So I will walk you through a bit through the general idea of this algorithm to build this data set. Basically, what we will do is that we will generate questions. For now, we are not even looking at images or OpenStreetMap or anything. We will just generate questions that we can answer with OpenStreetMap. To give you an example, in OpenStreetMap, you have static objects that are referenced. So for instance, streets, buildings, all of that. But you don't have cars. So if I ask, is there a car in this image? I know that I will not be able to answer to this question looking at OpenStreetMap data only. But if I ask, is there a building in this image? I know that I will be able to answer the question looking at OpenStreetMap data. So we looked at all of the objects that were referenced on OpenStreetMap. We made an algorithm to build the question. And then you take an image, you select the OpenStreetMap object in the image footprint, and you will answer the question automatically. So as a remember, that's what we need. First, an image, a question, and an answer. And we want a lot of samples like that. So as I said, the first part is to try to build a question that we can answer automatically with OpenStreetMap. So we looked at all of the elements that are referenced in OpenStreetMap. So for instance, you have road, water area, buildings, all of that. And we will select one randomly. In this case, religious building, religious place. Then we define some attributes catalogs. So for instance, attributes on the shape or on the size. So I could ask about circular religious place. You agree that if I have the vectorial object that represents the religious place, I can compute if it's more or less circular. That's quite easy to do. We have relation catalog, so positional spatial relationship between different objects. So for instance, now I will ask about buildings that are above a circular religious place. And finally, we define 4 types of questions: counting questions, comparison questions, presence question, and rural-urban questions. So comparison question, you have an example. Is there more buildings above a circular religious place than roads? So you will compare one type of object to another. Presence, you will ask, is there an object in the image? Counting how many objects in the image. And rural-urban is simply like, is this area rather rural or urban? And finally, we decorate the question as in a question mark and in the image and all of that. So you agree that this is a completely stochastic algorithm from which I can generate as many, like almost an infinite number of questions, which is quite nice. And all of these questions, I will be able to answer to them looking only at OpenStreetMap data. So let's take again this question as an example, and let's try to answer it for this image in Amsterdam. I was in the Netherlands back then. And we want to answer, is there more buildings above a circular religious place than roads in the image? I will not look at the image, but at the OpenStreetMap footprint of the image. So I put the image as a comparison, but in our algorithms, we are not looking at all at the image yet. And we will just parse again the question tree that we built previously. So we started with religious places. We have 2 religious places in this image, the big church here and a smaller one here. And again, we were interested in circular religious building. So the one that was on top is not at all circular, but this one you will agree that it's quite circular. Then we were interested in buildings that are above a circular religious place, so I highlighted all of the buildings in the image, and we will only select the ones that are above the religious place. And finally, we wanted to compare to that with the number of roads. And again, just using simple GIS operation, I will be able to answer the question, which in this case would be yes. Okay, so with that, I know how to generate as many questions as I want, and then for each question, I can look at an image and try and generate automatically the answer to this question. So we took a lot of images, we generated a lot of questions, and for each question, we generated the corresponding answer, and that gives us a data set. So the first one that we did was a Sentinel-2 based dataset, only using RGB imagery, covering the whole Netherlands. So we have 772 Sentinel-2 patches, and we generated about 100 question answer for each image, which gave us about 77,000 question and answer. So in the end, I have 77,000 image question answer triplets. Remember, we calculated before that what I needed was about 80,000 for my baseline. And for instance, this is a question from the dataset. What is the number of water areas? And in this image, it would be 7. Then later, so this was our preliminary study. We didn't know if it would work. Spoiler, it worked. So we wanted to try to use a bit more advanced datasets, and we wanted, advanced methods, and we needed bigger datasets with higher resolution. So we applied the same principle for high resolution orthophotos. And this time what we took was orthophotos coming from the east coast of the US. So you have an example of orthophoto here. We took 10,000 VHR patches. And again, we generated about 100 question answer for each image. So this gave us about 1 million question answers to work with. And again, an example of a question, what is the amount of buildings in the image? And that would be 7. I will mostly talk about this one that we call RSVQA high resolution, HR, from now on. And so again, I told you it comes from the east coast of the US, so you have the samples from the train validation and test set. As you can see, so this is Manhattan in New York City. So we mixed up, like we didn't do a geographical separation of train validation and tests. We have some training samples a bit from other places. Here, we also took from Rhode Island, I think, train validation test, but also to test the generalization capabilities of our methods, we did a separate test set that we will call test set 2 in Philadelphia. So in Philadelphia, we only have test images. We don't have training samples, no validation samples. And in this dataset, we had 4 types of questions: canteen presence, comparison, and area. So asking about the area of the area covered by buildings, for instance. And this is a repartition of questions and answers. So you have inside the 4 types of questions and all of the possible answers to the different questions. So for instance, you can see that for counting, I didn't put the label because they don't fit, but here, this is the answer 0. The majority of counting questions have the answer 0. Because of course, if you ask about a random object somewhere, the answer will probably be that it's not there. So that's the majority answer. And then we have decreasing distribution the higher we go in the numbers. So it's quite imbalanced in terms of answers. The questions we have, it's not 25% for each type of categories, but it's kind of balanced in terms of answers, not at all. We'll see later that this is a problem. Okay, that's the end of the dataset part for this paper. Are there some questions at this point? don't hesitate to interrupt me and, okay. Super clear from now. Nobody sleeping from yesterday? Good. Okay, let's go to the models. And again, we are going to try to define a model that we can work with this type of data. And we have two inputs, the image and the question, and one output that we are trying to get the answer. So let's start with the first input, the one that we are the most used to deal with, which is the image. What we want is to take the image and to try to extract a feature vector that will be an abstract representation of the image. I'm pretty sure that you all did that at one point in your studies, or even maybe this week. Basically, we will use a simple convolutional neural network to do that. So again, like this part was done in 2018, like Transformer existed, but it was really recent. So we used ResNet 152 pre-trained on ImageNet. We froze it, and we obtain a feature vector that will kind of represent the image. Then we have the question. So we want to work with the question. I don't know how much you learned about sequence handling for natural language. But basically, again, at that time, transformers were basically non-existent. What we used was bidirectional LSTM. So basically, you take your question, okay, here, is there a blah, 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 and you will encode separately each token. So first you take your is, you will pass it through a fully connected layer, a simple linear layer with some activation function, and you will obtain a feature vector for is. And then you continue with there. So there will take the second component, will take both the word and the previously defined feature vector. So it will know that there was is, at least the representation of is before. And you continue with the whole question. The problem if you do that is that, for instance, if we look at image, when you want to try to understand what is the meaning of image here, of course it looked at everything previously in the sentence. The problem of this type of technique is that if you want to understand there, you only have access to is, but not to what is coming up next. So that's why we used a bidirectional LSTM. Then we will take again the last word and pass it to and the representation of the last word that take into account the whole sentence, pass it to a fully connected layer and extract a representation, and do that for all of the words. So when we arrive here, we went to a lot of different fully connected layers that represent the question in both directions. And of course, so it has been trained. I will simplify a bit. It's not exactly that, but it has been trained to try to, for instance, do translation. Here, I translate my sentence in French, or to try to complete part of the sentence. So, for instance, is something a park in this image? We try to train the model to learn that something should be there. So that's an early form of self-supervision. In this case, it has been trained on book corpus. So it's a skip-sort vector model. Basically, you take a lot of books, you take a random sentence from the book, and you try to predict the previous and the next sentence, which is a super hard task. I invite you to take your favorite book, take a sentence randomly, mask the previous and the one after, and try to predict them. It's super difficult, like basically impossible. But it turns out that it's a nice self-supervision technique. And taking the last feature vector, we have the feature vector that represents our question. So now we have one feature vector for the question, one feature vector for the image. And of course, we want to have a joint comprehension of both feature vectors. So we would like to obtain a feature vector that encodes both the image and the question from these unimodal feature vectors. This is the fusion step, so the third step. There was first the image representation step, then the question representation step, and now the fusion step. And basically, what we did is to learn another fully connected layer for the image, a second one for the question, and then we take our two representation and we do a simple pointwise multiplication. Okay, we'll multiply each element of each vector, and we obtain a new vector like that. I will talk a bit later about why we did that. Like, you might think it's a bit weird to do a pointwise multiplication. I will show you a bit later why we did that and how can we do it better. So at this point, we have one feature vector that represents both the image and the question. And finally, we need to do the prediction. The prediction of the answer. In our case, we have two approaches for visual question answering. Either, that's the simplest one, we try to frame it as a classification task. We take a set of possible answers that will include yes, no, 0, 1, whatever. And we try to classify what is the most probable answer among this set of predefined answers. So this is a simple classification task. And the second type of approach is open-ended, generative. So in general, with autoregressive approaches, again, didn't really, like, that was not that common at that time. And we wanted to release something. It took me 3 years. We did always the simplest option. Otherwise, it was just too long. So we did the classification among a set of predefined answers. So we look at possible answer from the validation and trend set, and we put that in a vector, and we try to select the most probable answer from that. And to select the most probable answer, we take a feature vector representing both the image and the question, and we apply a simple multi-layer perceptron here, and we get our final prediction vector. Then we can apply an argmax on and get the most probable answer, which in this case would be yes. Then, of course, we compare it to the ground truth. And all of the fully connected layers that we need to train, basically in the last two steps, the fusion and the prediction, will train from a simple cross-entropy loss, classical classification loss. Okay, so this is the basic design of a visual question architecture, visual question answering architecture. We have 4 components: image, text, fusion of both, and prediction. Simple architecture. We applied that on our dataset that I talked about, the ASVQR HR. And we obtained some pretty interesting results. So again, you remember we have 2 test sets, one in New York that is close to the training points that we have, and one in Philadelphia in which we have 0 training points to test the generalization capabilities. And when we applied our model, we trained it and we evaluated on the test set, we got this type of answer. So for instance, for counting, we got 68% of accuracy. That means that for 100 question, 68 of them, we got the right answer. We trained several models to apply a standard deviation to evaluate how stable are the training process. That's what you have in parentheses. But then so 68 for counting, 90% for presence, comparison, is there more roads than buildings, 88%, and area, 85%. That's good, no? Like, I don't know what you think, but like, at least back then, like, if you ask, is there a road in the image, we had an algorithm that was able to understand what we meant and find the road in the image. And the nice thing is that, of course, when we were trying to transfer to a new domain, we were losing a bit of performances. For instance, if we look at the average accuracy, so the average of the 4 scores that you have here, or the overall accuracy, which is a weighted average based on the number of samples that we have in all question types. Like we lose a bit of performances, but not so much. In addition, a nice property is that when we look at the confusion matrix, we can see that even when we answer wrong, so for instance, is there a road in the image and the answer should be no, when we answer wrong, it's that we answered yes. We didn't answer 3 to is there a road in the image. So like even our wrong answer kind of makes sense from a semantic point of view. So that's what you have with the boxes, like they represent the different semantic classes. Let's look at some visual results. For instance, is there a residential building at the bottom of the place of worship? The ground truth was yes, because indeed we have a place of worship that we can see here. And the prediction was yes. It was working well. And this one, what is the amount of large buildings in this image? So let's imagine that this is a large building. Who would answer that there is one large building? Can you raise your hand if you think that there is one large building here in this image? Okay, 2. Who would answer that there are 3? A lot of undecided people. But thank you for the 5 who answered. So 2 answered 1, 3 answered 3. And funnily enough, like the ground truth was 3, which means that they were registered as 3 separate buildings in OpenStreetMap. And what our model was predicting was 1. So it kind of made sense, all of that. And the results were surprisingly good. And then we sent the paper to the journal, and a wise reviewer said, how good are your results? Could you try a simple test and try to replace the images? So you swap the images. So for instance, you would ask, what is the amount of large building? But instead of taking this image, you will take this one, but the ground truth would still be 3. So in theory, it should not make sense, and our performances should drop heavily, right? And what we found out is that when we did that, so things that absolutely didn't make sense, we still managed to get about 70% of accuracy. So that was a bit sad. Basically, we had an algorithm that we thought was working, but it's because, as you have seen before, our dataset is very biased. That is, when you ask the question, how many something is there, if the model is not sure, it can just answer 0, and about 50% of the time it will be right. So that's a bit an issue. Okay, this was the first paper. We just have these papers to cover from now on. Are there some questions at this point? And yes, so Sergio.
Thank you very much for the presentation so far. Just a very simple question, as I'm not into RSVQA. Is there any reason why the ground truth is compared with all of the sets of possible answers? Or would it make sense to have like the different kind of answers separately to train a model for every type of question? I don't know.
That's a great suggestion. We did it. I will talk about it. But that's a really good idea, in my opinion. Yes.
Maybe you mentioned it, but I missed it. Why was the counting task less accurate than the others?
It's actually, so that's a very good question. So there are a lot of reasons. Historically, in visual question answering, even on natural images, that's a difficult question. I will talk a lot about it in the following up. But basically, the point is that we are trying to do counting using classification. So if you answer 3 when the answer should be 2, you would be penalized the same as if you answered 42 when the answer should have been 2. Like classification is not at all adapted for regression. And that's why actually, you know, like for large language models, it's also quite often like a test that people are doing. For instance, like the classical tests that you probably all have seen is to ask how many R's are there in the word strawberry. This is super easy, yet LLMs often are not capable of answering this task. It's a counting question, and like models are bad at this type of questions. Yeah. Yeah.
Thank you for the presentations. So I am also like a follower of the counting situations. So in some Google Earth image or any kind of ortho images, you can see some in residential area. In top of view, you can see a single building structures, but actually there are multiple structures are registered or a city office or something. So how you did answer these questions? Like let's say in counting your objects, you show in the last image, it shows as a 1. But let's say it was a huge building, but it could be like a 14 or 10, something like that. So how did you answer these questions?
Yeah, that's a great question. Basically, like if I extend a bit your question, the point is that we'll never be able to get to 100% accuracy because we are using super precise data that has been done by people who walk on the street and who have access to aerial images. And we try to answer them from aerial imagery that is sometimes not super well resoluted. So there are things that we just simply cannot see. Like in your case, things from street view. So if we wanted to accurately answer this type of questions, for instance, we need to have access to street view imagery in addition to the remote sensing imagery, to the aerial view. And that's multimodal visual question answering. I will also talk a bit about it later. Thank you. Okay, yes, another question.
Sorry, yeah, thank you for the time. I just want to have a silly question. In the label datasets, would you be possible to also adding some non-value classification? So to say, if the question is gibberish like blah 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 blah, the model will be understand this is a gibberish question, so it will be void kind of training process at the end.
Yeah. So it's kind of linked to the previous question. Like in some cases, we shouldn't be able to answer, and it would be nice to be able to abstain to answer. And that's also, I will not talk about it, but there is a small project that we did about that. The results are coming in a book chapter that we are writing with Lucrezia, and that is edited by Ronnie Hench, who is organizing this school. So answer soon in this book chapter. Okay, thank you very much for the question. I will continue on the other parts, on the other papers, and again, I will look a bit at the same structure. We will first look at the data, and then the models. So, more data and more models. Let's look at the data first, and there are a lot of reasons why people might want to build new data sets. Like we highlighted some of these reasons to increase the geographical diversity. Again, if you remember, the first data set, low resolution, was in the Netherlands, a rather small country, and the second data set was in a small part of the east coast of the US, so that's really local data sets. To increase the question diversity in both data sets, we only had 4 types of questions. To add capabilities, multimodal, we were talking about it, and to have a better balancing because we saw that it was an issue. So I will start with the diversity, both in terms of geography and in terms of questions. And so again, if we look, we have these 2 data sets. And we asked ourselves, can we do better? When we finished this work, like the first version, it was end of 2019. And I tried to remember, like 2019 is not so long ago, right? It's 6 years ago. And I tried to remember a bit what was the situation. It was hard to get a clear picture. So I looked at reviews of the time. So reviews are also useful from historical perspectives. And I found this review paper that was listing the data sets that were available in remote sensing in 2019, 6 years ago. Like, I don't know about you, but me, I was a bit laughing when I saw this table. Like, look at the number of samples of each data set and the number of data sets. Now you have so many data sets that I think GRSS did this EOD website, Earth Observation Database, that I use a lot. Thank you, GRSS, for that, by the way. But you have so many more data sets today that you, of course, like, I guess nobody knows all of the data sets that are available in remote sensing. At that time, it was this list. So we were quite restricted in terms of data that we could use, and actually 1 million sample was like a big, an order of magnitude bigger than what was available, but we wanted to try to go to a different scale. And again, and for that, we discussed a bit with Begum Demir, so I know that some of you know her from yesterday's gala dinner's discussions. And like, it was, like, datasets were such a problem at that time that it was the topic of an ERC grant. Like, ERC grants, you know that it's hard to get. And she got an ERC grant to do a dataset that that has been and is still super useful to the community. Like, that's a great dataset, Big EarthNet. I'm sure that some of you have used it. And we try to see, there is this great dataset with millions of images. Can we use it for visual question answering? So basically, what Big EarthNet is doing is to link Sentinel-2 images with coin land cover labels, so land cover classes. So for instance, you will take this Sentinel-2 image and you will have the following label, discontinuous urban fabric, and so on. If we look at this list of labels, you can see that it's quite easy to ask questions about the image. For instance, we could ask, is there a broadleaf forest? We can look at the list of labels, see that it's there, and so the answer, we can create it automatically from the list of labels, will be yes. Same, is there a permanently irrigated land? We look at the list of answers, no, right? And then we can try to build a bit more complicated question. For instance, is there a broadleaf forest and a permanently irrigated land? There is a broadleaf forest, but not a permanently irrigated land, so the answer will be, again, no. But that starts to be a bit harder because you need to understand the logical operation end. So that's what we did with this dataset as VQA meets Big EarthNet. And in this case, so this was also, I think, end of 2020, if I remember correctly, and it was 590,000 images, 15 million question and answer over most parts of Europe, because the Coin Land Cover project span Europe. And so it allowed us to have better geodiversity, other questions, other type of questions, also to try to predict land cover. So for instance, what land covers can you see in this image beside forests, and this type of questions. And I will not go over all of the datasets that has been created after. I did a small summary here, but as you can see, a lot of datasets with different image resolution, sometimes very, very high resolution, different number of images and number of questions have been created. And so now you can have datasets that cover a large part of the world and also interesting questions. So for instance, FloodNet, which is highlighted here, you have this type of questions. So you have an image, and you will have question, what is the overall condition of the given image? It's non-flooded, so it's, as the name suggests, about floodings, which is an interesting task for visual question answering. Okay, added capabilities. So for instance, multimodal. We saw that it might be interesting to not answer only from optical images, but you all know that there are different type of modalities that can bring different operations. And I will talk about the work of Lucrezia here, because Lucrezia worked a lot on that. That's the main topic of her PhD. So this is a paper that has been recently accepted. Congrats, Lucrezia, and congrats on the name. Love it. And what she did was, again, we had BigOfNet. So I talked about it. We did this SVQA meets BigOfNet dataset. And a few years later, Begum released BigOfNet multimodal. So it was taking the same labels, but in addition to the Sentinel-2 images, adding Sentinel-1 images. And we thought, there's something to do here. Let's just take the SVQA meets BigOfNet, merge it with BigOfNet multimodal, and we have the dataset SVQA meets BigOfNet multimodal. Like, of course, it sounds simple here. It's actually quite complicated to do in practice. And we have then questions. So, for instance, is there a water body? You might know that it's easier to use SAR to detect water. So typically, it was nice to, like, if I just show you this image, you might not know if that is a water body. For instance, in the Netherlands, it really could be a small water body. You can see on SAR that it's not. They also, so with Lucrezia, with Isham, another PhD student, we did another data set that was presented at Earth Vision at CVPR this year. For instance, if I show you this image, do you know what can we see on this image? Like, where is it first? What? A city, yeah, which one? Yeah, that's a bit, I'm stupid, I should not have put Paris. But, yeah, so that's actually Maison de la Radio, like a famous building in Paris. So, but some of you have found that it's Paris. If we zoom out and we look at Sentinel-2 imagery, I'm pretty sure that now most of you would have found that it is Paris. You might be able to see the Eiffel Tower here, and yeah, you might have seen Paris from the sky before. So we built a completely new data set with orthophotos, so very high resolution images. And in this case, we use Sentinel-2 and Sentinel-1 to provide context. Okay, so you have the white rectangles that show the footprint of the orthophoto in both type of imagery. Of course, in this case, Sentinel-1, we didn't take square pixels, so that's why it's a rectangle and not a square. And then we built a lot of questions. So we have 21 types of questions in this data set. And we trained some models on that. You also, so we talked about multimodality, but for instance, the team of Xiao Shangsu in Munich, they did change detection with visual question answering, so asking about changes, which also requires pairs of images. So for instance, what are the region of buildings in the pre-event image? This one mainly changed to, this one. And using the labels, they were able to compute automatically that it was low vegetation, and then they trained some models to answer this type of questions. So that starts to be a lot of tasks that we can do with visual question answering. Of course, at the end, we would like to be able to do any type of task, but we saw with flooding, we saw with change detection, we saw that we can use multimodality. There's still the issue of the balancing. If you remember, I told you that the balancing was leading us to think that our models are good when they are actually not that good. So, yeah, these are the results that we already saw. And as I told you, if we put a random image instead of the real one, these are the results that we get. So instead of 83% in New York, we have 73 and 72.5 in Philadelphia. So that's really not such a big difference, and it's kind of disappointing for us. Because in this image, there are clearly not 7 buildings, but yet, because we have these biases, we have good scores anyway. And these biases are a super common thing when we deal with language. If we look at the answer distribution, And be careful, as it's written, it's in log scale. These are the answer distribution, starting with the most frequent answer, and so you can see that is dropping very fast towards like close to 1, 2, 3. Yet for the most common answer, we have thousands of samples. So she did a huge study about that was recently published in Geoscience and Remote Sensing magazine. But language biases, I will not present the whole study because it's quite complete. But basically, what she did was to define some scores that we can use to assess if a dataset is biased or not. And to do that, we look, for instance, at the most common answers, the number of possible answers. So in this dataset, we have 222,000 samples, 55 in total possible answer, and the most common answer is no. And then we can look at what score you can get by just learning the biases at the question type. So basically, you will have a model that would be able to identify the question type. Is it a counting question, a presence question? And learn that the most common answer for a counting question is 0, the most common answer for a presence question is no. And doing that, on the whole dataset, we would get 38% accuracy, on area 62%, on comparison 67%, and so on and so on. Now, that's the score you would get if you had a dataset, a model which would not be influenced by biases. That is, it would take all of the possible answers for a question type. So for instance, area, we have 5 types of answers, and would answer one of them randomly. So we would get 20% for area because we have 5 possible answers. And finally, this is the dataset score that will basically be a function of how close are these two. Like ideally, we would like these two scores to be as close as possible. And of course, she also defined some metrics to evaluate the models based on the dataset biases. So trying to take out the bias from the equation of the evaluation. And then, so this was a work done by Christelle Chapuis, who I was co-advising at EPFL. She recently defended a thesis a few months ago. And Lucrezia went to visit Davis at EPFL, and they worked together on a project that was led by Lucrezia on a new data set and a new method that would be like where they try to really take care that there are as little biases as possible. So again, you can look at the paper for more info. As expected, I'm a bit late, so I will jump to the models. So, you remember this figure? These are the 4 main components of a RSVQA model. We'll look a bit, again, at all of the components and see what people have been doing for each of them. So here we were using a simple CNN, but when we look at what do we expect from a good vectorial representation of our input, image input, what we would like is to get a representation that is computing, taking into account the resolution and the modality. So for instance, we want to know that we are using high resolution images and optical, or lower resolution images that are SAR images. And for that, there are a lot of different works that have been published. So for instance, using multi-scale networks to try to take into account the different resolutions, object-based feature representation. So for instance, because the questions are often about objects, is there a building, is there a road, all of that, Raphael Felix and his colleagues were using an object detector to extract the features of the different objects. And of course, more recently, there were transformers that were used also for the vision part. A second part that we would like is that the feature that we extract are relevant for the question. So for instance, if I ask, is there a road in the image, we don't care to retain features that represent buildings. It should not be useful to answer the question, is there a road in the image? The thing is that in this part, so far, we have only seen the image. So actually, this is something that we do at the fusion part, so I will come back on the feature extraction part at the fusion part. Okay. Then for the text encoding, so the text feature extractor, Christelle did a study on the best practices that we can use to extract text representation. So for instance, she tried transformer, she tried if fine-tuning was helping, and actually using transformer, like the conclusion of our study is that using transformer instead of simple recurrent neural network is good, but only when you fine-tune them. And the thing that we found out is that when you fine-tune your model on your dataset, so the textual representation on your dataset, of course, it increases the biases, because the model can much more easily learn that if it's a canteen question, it should answer 0 and all of that. Let's look at the fusion now. And I told you that, so we have these two vectors, one for the image, one for the question, and I told you that what we were doing was a pointwise multiplication. The reason behind that is that what we would like to do, we would like to have a perfect interaction between these two vectors. So that each, like I will use a word that I was not planning to use, but each dimension of this vector attends to each dimension of this vector. And like an attention mechanism, you might know that this operation is actually quadratic. We need to do a matrix multiplication between the two vectors, and then we get this matrix representation. And the thing is that if we do that, we have a feature vector that is like the square of the dimension of each input feature vector. So here we have feature vectors that are about 1,000 in dimension. So that would mean that we get a feature vector here that is about 1 million in dimension, and we needed to put that as an input to a multi-layer perceptron. And that hurts a bit when you have 1 million elements as an input to your MLP. So this is not doable like that. We cannot do this matrix multiplication. So of course, a simple strategy, we don't see it super well here, but is to take the diagonal. And then this is actually our pointwise multiplication. A second strategy was proposed with the MCB algorithm. Basically, you will make a simple linear combination of your vectors to a slightly higher dimensional vector. So for instance, you will do first one plus fifth one minus, I don't know, 20th one. And you will define like that about 1,000 simple operations that shake kind of your vectors, your input vectors. And then you will do a simple pointwise multiplication between the two vectors. This has been shown to increase a bit the interactions between the both vectors. Like it's actually a convolution, sorry, between both vectors. And finally, one operation that was proposed, which is actually a kind of attention mechanism, is to use the Tucker decomposition. So basically you do a convolution between both of your vectors, you do it several times. We come back on the multi-head attention mechanisms for those who know it. You sum everything and you get your representation of a lower dimension. So these last two types, you can see it as, like these last two methods, you can see it as type of attention mechanism. And that actually answers the question, we should extract features relevant from the question. To do that, we need attention mechanisms. And that's what people are often doing nowadays. All of these different solutions were again studied by Crystal in this article here that you can read as a reference. And finally, the prediction step. So we said that we are doing classification from a set of predefined answers, and there was a question about that. It's not good to predict numerical answers. So for instance, what is the number of buildings? The answer should be 42. And if you remember, we have this multi-layer perceptron. So we will go through our multi-layer perceptron and compute, for instance, 42. And the problem is that if we get it wrong and instead of 42 we get 43, we'll penalize exactly the same as instead of 42 we get 12. That doesn't make sense. That's not good. 43 is a much better mistake than 12 in this case. So what we wanted to do is to apply a regression loss on the numerical prediction. And to do that, we did a 3-stage prediction method. So first we take the feature vector coming from the fusion, and we'll try to classify the type of answer that is expected. So the answer can either be a classification type of answer, yes, no, for instance, or a numerical answer, right? And then we will have 2 branches, one that is classification, so it will try to predict, for instance, yes or no, and a one that is not segmentation, sorry, regression, a regression branch that will try to predict a number. And we will decide which one to keep from the output of this prediction. So we'll predict both information, but we'll keep just one of the two based on the type of question that was asked. And this was a paper that was released a few years ago. I mentioned it earlier, there is the classification approach, but of course there is the autoregressive approach. Autoregressive models, I don't know who here has trained an autoregressive model from scratch. It's a bit complicated. So we didn't experiment with that, but actually last year Google released a PalyGemma model, and they contacted me to tell me that they were applying it on our dataset. So I was cool, like that would be a new relevant information. Basically, they are doing exactly what you expect for multimodal transformer. They will convert the image into tokens, the text as well into tokens, put everything in a VLM, and generate an answer based out of that. And they got some results that are here. So you might not have the number in your head, but what I was showing you before was models that were reaching about 83% of accuracy. At that time, the best models were at 89. So in 5 years, we went from 83 to 89, and all of a sudden, there was a model which was super generic. They tried on visual question answering, and they got close to 93% of accuracy. So super impressive, right? Like, big jump. Actually, when you look into details in the paper, that's what you can find in the appendices. So for instance, for SVQA low resolution, train, we use 47,000 samples, and we took the non-numeric samples, train and val splits. So they train on train and val, and they removed all of the counting questions. Also for the evaluation. So you have an evaluation that is not on the same test set, and that actually exclude counting. So that's also a solution to exclude, like to deal with the difficulty of counting question. You just exclude it, hoping that nobody will ever ask for a count. I don't think that's the good approach. But yeah, basically it's a difficult task, even for autoregressive models. Okay, we looked a bit at the different components. I have a few more things to show you. First, on data augmentation. You know that data augmentation is absolutely essential for training deep learning models. In the case of visual question answering, if you want to work with that, you just need to be a bit careful. Because for instance, here, you have the question, is there a park on the left of this image? And the answer is yes, because on the left part of this image, you have a park. Great. What do you do often for data augmentation? Rotation, flips, these kind of things. Let's rotate the image. Is there a park on the left of the image? Not anymore. It's on the right. No, it's here. So we need to be super careful when we do data augmentation. We cannot use classical image techniques, like the traditional flip, rotation, crop. They do not work. There are a few techniques. So the first thing that we did was to spot the spatial descriptor when there was left, north, west, south, bottom, all of that. We were not modifying the, like, no rotation, no flips, nothing. A second approach is to do, for instance, back translation. So you will take your question in English and translate it, using, for instance, DeepL, in French. Not super useful so far, but then you can translate it back to English. And because the translation is not a bijection function, you will get a slightly different results for your text. So that's a way to do data augmentation on the text. Another way is to use large language models. That's what Ishan did recently. So basically, you ask a large language model to reformulate the question, and you will get like a question that has the same semantic meaning, but in a different manner. So for instance, if there is a park on the left of this image, of course, the answer to can you see a park in this image is yes. So just be careful a bit about data augmentation. Let's go back to our pipeline, and I will show you one last type of pipeline that is a bit different. So we start again with our inputs, but that was a work that we were doing in 21 with Crystal. And at that time, even though ChatGPT was not existing, large language models were already a thing. There was BERT. It was like starting to be a hot topic. And we thought, okay, if large language models are so good, can we leverage them as the base of our reasoning model, like our reasoning capacities? So we thought, okay, let's try to convert of our image into a textual description using, for instance, classes of interest and all of that. And then we will put our question to a large language model along with the textual description of the image. And once you have that, like, no, again, you have all experimented this kind of thing with ChatGPT or equivalent. Like, in this case, it was an encoder-based model, BERT, so we get a feature representation and we had still to do the prediction. But you can get an answer to your question using basically almost only a large language model. And this is a family of models that we call prompt RSVQA. It was presented in the summer of 22. And it has been used in a lot of different ways. Because the advantage of this type of model is that, A, it increases a bit the interpretability. That is, if you get a wrong answer, you can look, is it because there was a misunderstanding at the LLM, in the LLM part, or is it because the image representation, the textual image representation, is not abstract anymore, it's something that you can understand, was wrong. So for instance, if in the textual representation you had, there is 2 buildings and actually there was 1, you know that the problem comes from your visual part. If the textual representation is good but the answer is not good, you know that the problem comes from your LLM part. As you might guess, the problems often come from the visual part, which is great for us because we prefer, at least I prefer to work on images than on text. So it means that there is more work to do for us on text, on images. And it can be adapted with vision language models and foundation models. So for instance, here you have visual foundation models that can extract a lot of different type of information and that we can put as an input to a VLM. Or again, the paper that Lucrezia finished recently, Checkmate, that works a bit in the same way, except that in this case, we also predict the parts that were used to answer the question. So we have, in addition to the interpretability, a level of explainability. 10:59. I have 1 minute to conclude. I will take a bit more. So I hope that, like, as you can see, a lot has been done in the past 5 years or so on this topic. What I hope from today is that A, you find this topic a bit exciting, and B, maybe some of you will work on it in the future. That would be super cool. I think there are still a lot of things to do on the topic. So for instance, as we have seen with this PalyGemma paper, numerical answers are still a big problem, to the point that it's not only PalyGemma that is excluding them from the evaluation. A lot of papers are excluding them from the test, saying that it's too complicated, we exclude them to be able to report high number. It's a bit a pity. So numerical answers is still a big part of work. Multimodality, so it was the topic of Lucrezia's PhD thesis, which she will finish very soon, hopefully. It's still not solved. Despite the amazing work that she did, it's still not solved. So there are a lot of things to be done. For instance, working with street view images, we have seen with the questions that it was probably useful. There are a lot of things to be done. The time dimension, even though we saw that there was a change detection dataset, is left very much unexplored. So for instance, if you come back to one of the very first questions that I asked, I would like to buy a building, I want something that is not modern, an area that is not modern, so I want an area where no building was built in the least amount of building were built in the last 10 years, something that we are absolutely not capable of answering because we don't know how to deal with big time series. And weirdly, there are quite a few models that look at typical remote sensing questions. So for instance, I'm sure you have all your topic of interest, but hydrology, agriculture, these are things that people do a lot with remote sensing and that are actually completely left away from all of the data sets that we used. And of course, foundation models. People are working a lot on foundation models. There are some adaptation to visual question answering. It's often like a task on which they are examined, but there are no specific models that use these foundation models in an original way. I would like to thank you for listening. There is a QR code here on which you can download the slides. There are some links on resources to start with. So for instance, the links to the datasets that I talked about in this presentation. And there are also the links to the labs, but don't look at them now because Lucrezia will do a presentation on that just after. I would like to thank you, but also to thank the PhD students that I worked with, the other colleagues that I worked with, and in particular, all of the ones that were involved on these visual question answering questions. So if this presentation exists, it's mainly because of them. Thank you very much. I don't know if there are questions here.
Thank you very much for your nice presentation. I can understand the questions you have came up, but another kind of questions that are interesting for me would be like, okay, on this scene, what is the economical potential of the scene? So the question is, what does it take to get to that point, to get a model which is which can say, okay, this is the potential, the economical potential of this scene, for example?
Yes, that's an interesting question. I think one way to do, so basically you will not be able to do that reliably just from images, right? You could get an answer, but it will not be reliable. I think the answer to that, I didn't talk about it here, but will be this agentic AI. We presented something on this line at LPS this summer. So basically, something where you ask this question to a large language model that has access to a lot of different functions. For instance, downloading files that will describe the history of the GDP in an area, downloading the shape files that will describe the evolution of the area in terms of morphology and urbanization, and we'll be able to, for instance, look at research articles, how to estimate the potential of an area. So it will be more like these agentic AI approaches that are a bit more advanced. It's also a nice area of research, but I think like this type of question calls for a different type of models. Yeah.
Okay. Any other question from the audience? Don't be shy. We have just a few minutes more.
It means it was super clear.
For sure. I have a question, more a curiosity. You talked about, I remember the first part of the lesson when you presented the way to extract features from the image, and you used the ResNet, but frozen, using the parameters from ImageNet. So this is not optimal at all. Then you presented several strategies to address even this point. You talked about even the extraction of the feature from the text, and you told us that fine-tuning in this case can help. But on the other side, did you test even some strategy to fine-tune the ResNet, or you just changed the way to extract the feature and to collect directly together, fusing together with the text part? And if so, you measurement the performance, because I don't remember if you show this, if there is which is the gap in performance that you can obtain. So if it's relevant to improve this part related to the image, and what the gain in performance that you can get in extracting in a better way the feature from this branch.
Yes, thank you for the question. So indeed, like it's a bit weird to use ResNet on ImageNet as a pre-training. I didn't test this, like to try to fine-tune it. I didn't try other sizes of ResNet because again, we were kind of doing the simplest method at each point to release this. But Lucrezia did, actually, in one of her first studies. And weirdly, for optical imagery, the results, Lucrezia, you tell me if I'm wrong, was that ResNet 152 pre-trained on ImageNet was more obtaining better performances than to pre-train on BigEarthNet, which, like, it was a bit the point of BigEarthNet to serve as a pre-training, like it was kind of the remote sensing ImageNet. In this case, it was not working. So that's a bit surprising. We don't know really why. I was super lucky that the simplest solution was actually the best one. But yeah, so it's a part that we don't really fully understand. But because on SAR, for instance, the results are a bit different. So it depends on the type of modality, how far you are from ImageNet. Also, ImageNet will have much more diversity in terms of features, so maybe it's a bit more interesting for large models. Yeah.
And this is aligned with one of my finding in another problem was practically the same. So it's better to use ImageNet. Maybe it's more general. It's able to extract more general features than use a customized dataset for the fine-tuning of the backbone. So
Yeah.
it's practically
Yeah, yeah.
aligned to your finding. So, any other question? Okay, if we have no other question, we can proceed with the break, the coffee break.
Okay, people, so let's restart. So hopefully you enjoyed your coffee break, and I hope it regenerated you a bit so that you will be ready for this practical work on visual question answering on remote sensing images. So I decided to divide this practical into 3 parts. In the first part, I will introduce to you TAMI, that is called Text and Multimodal Imagery, and it's a dataset that we developed. In the first part of the practical, you will explore a bit these datasets, but first, of course, I will introduce you to it. In the second part, you will use a model that we developed called RSVQA, Multimodal, Multi-Resolution Remote Sensing Visual Question Answering. And hopefully, if we'll still have some time, we will explore something a bit different, so Quen2VL, because as Sylvain already told you, you can do VQA into a different way, seeing the task as a classification task or with decoder-only models. So let's start with TAMI dataset. No, first let's start on why we created TAMI dataset. What is the idea behind? The idea behind is that at the beginning, most of the dataset in RSVQA had images that were optical and very high resolution. But even though with some certain type of question, these images work very well, for example, for counting, presence, area, with some other questions, these images have some difficulties to answer. For instance, if the question is, what is the flood risk level in this image? The answer of a model, but I guess also your answer, would be that the risk is low, because you cannot actually see any water body in this image. So why would there be any risk? But if you take a look to a more context, you can actually see that this very high resolution image is in an area very close to a river. Hence, a model, as I guess a person, would actually say that, okay, this area has actually a high risk of flood. So we understood that there was basically a need of a dataset in RSVQA that not only had very high resolution optical images, but that could also include different resolution and different modalities to have as much information as possible, basically. And for this reason, we introduced TAMI. So how we created TAMI? The main idea is that we took BDORTO data that are very high resolution images provided by IGN. The resolution is 20 centimeters, and some areas have a resolution of 15 centimeters. We divided these huge images into patches of 1,000 per 1,000. And once we have done that, what I worked on is that I basically found the corresponding position that correspond to the center of the patches in both SAR images and also Sentinel-2 images. Of course, the process is slightly easier when working with the Sentinel-2 images, while with SAR images there are a lot of pre-processing steps that one needs to do. But the idea is that the center of each patch corresponds to the same location, and then a user can decide how big he wants the patch to be, depending on the task. So how much context the user needs for its task. If you're wondering why the Sentinel-1 image is a bit colorful, it's because we decided to use VV, VH, but also the ratio between these two polarizations, since we noticed that in classification task, the ratio is useful to classify volumetric information. So we decided to keep it. For the creation of the question and answer, we took the same patch that we used for the creation of the triplets of images, But we also used some external data, such as IGN BD-topo, that are basically vectorial data that describes in a vectorial manner what there is, like in a street, so how many buildings, how the streets are organized, etc., etc. We also use the flooding risk database to include questions about floods. The urban units 2020, the cone inland cover map, to also add question about city organization and classification question of what there is on the ground. And also the European mountain areas. We then created basically 10 questions per type per patch, ending up with a huge amount of question and answer. And as Sylvain already anticipated, it's very important to have a balance in the answer. Otherwise, one answer may appear many, many more times than another, and then your model will be strongly biased. And for this reason, we applied some balancing technique to have a more balanced as possible of a dataset. The region that we decided to take into account in this dataset are mainly, let's say, free. So the area of Ile-de-France, so basically Paris and its suburbs. Then we consider Haute-Savoie and also Hérault. I hope the pronunciation is correct. And we did so because we wanted a geographical landscape that's more heterogenic as possible, to have both coastal area, mountains, and also urban and suburban. So finally, what we ended up with in terms of question and answer distribution is something like this. So we have 5 main classes of question that are then divided in 21. And inside all the boxes, you can basically see the different answer and how and their distribution. So you can see that the distribution is quite well done. Of course, again, as Sylvain anticipated, there are some answers that are slightly more present in the dataset, such as 0.00 meter or 0%. So yeah, as Sylvain anticipated, this type of answer, so the 0 tends to appear more, but we tried as much as possible to balance it. Okay, so in the end, we ended up with a dataset that contains almost 283,000 images, BD-ortho, then there are the SAR and multispectral. More than 3 million question-answer pairs, 21 different question types, and almost 110,000 unique answers. And yeah, here you can see basically all the dataset. So multispectral, BD-ortho, also the segmentation maps that we created using only some classes of the BD-topo data, the SAR image, question answer, etc. So the idea now is to start working a bit on the code, so to exploring the dataset a bit. Here is the QR code, but probably you already have the link on the WhatsApp group. It will take you to a drive folder, and what you can do is basically right-click on the folder and add a shortcut to your drive. We will work on a subset of the dataset that includes only 30 images. BD-ortho, then there are of course the SAR and multispectral one, but it's a very, very small subset of the dataset. What I would suggest is that maybe you can work like in small teams to not have problem with the Wi-Fi as the other days. Okay. Okay, let me know if there are problems, if everyone is able to access the code. All good? Okay. Okay. So maybe I will start now. Okay, so the idea is that I will go briefly through all the code, and then there will be some parts inside the code that have like written code that you will have to complete. Don't worry, there are not many, and they are quite straightforward, but it's just to make you like explore a bit how it works and understand it as much as possible. Okay, so first of all, you need basically to mount your driver to have access to the data. Then you will have to install Rasterio, install all the libraries, and an important thing is that inside the folder there is this code, sar_display.py, that you need to import inside to basically visualize our images. So after you've done that, you can run the imports of all the packages. You can then check that everything is working fine, so you should have all of these different data. You will have to save the base folder as such. And then here there is again a bit the introduction of the dataset and the different modalities and images that we have used. Here there are also more information, so it is a bit more detailed on like the classes that are present, the type of, for example, SAR image that we used. And okay, at this point you will really start to explore the dataset. So first of all, you will have to run this cell that will show you a very nice picture. I don't want to spoil it because I want you to do it yourself. Once you have done that, you will have to do basically the process that I have done to find the same, the latitude and longitude corresponding to the central pixel of the Bede-Orto image. So no, don't worry, you don't have to basically guess the coordinate reference of the systems because it is already, it's already in the code. You will just have to complete like here. Once you will have found the latitude and longitude, you will move basically to retrieve the correct position of the x and epsilon y of the Sentinel-2 patch. And finally, you will be able to plot the corresponding patch in Sentinel-2. Then a very interesting thing is that you will have to do something similar also for Sentinel-1, but it is a bit more complicated with Sentinel-1 due to the geometrical distortion that are present in this modality. So to retrieve the same position, you also need the altitude. And to do that, we use this API that comes also from the IGN. Here, basically inputting the latitude and longitude, you will be able to extract the altitude of a location. Unfortunately, we don't have enough time to go through all the process that you need to actually extract the same position in SAR because there are a lot of correction, orbital correction and stuff. So I already provided you with the right position here, so pixel position. And then I'd like you to explore a bit the dataset. So what you have to do is just change this index and see different images. So you will see something like this. You have your Bede-Orto image, the corresponding Sentinel-2. in RGB and all the other bands. And then also in Sentinel-1. And then finally, you can also explore the question and answer that are present in our, yeah? Okay.
The SAR display package, it says there's no module like...
Yeah, because as I said, here in the folder, you have the file. You have to just upload it and put it inside. Okay. And then you will also be able to basically explore the different question and answer. Again, the idea is that you will modify the image ID and then also the question and answer ID, and the output will be, you will have all the information about the image that you have chosen, and then the question and answer corresponding to the index that you have choose here. So I would say that maybe I can like give you 10 to 15 minutes, and then we will see together if there are problems. Yeah, it's mostly like an exploration of the data set. Okay, not even if you like divide in groups, because maybe it's a bit... No, they don't have to download. So yeah, you don't have to download the dataset. If you just add it as a shortcut to your drive, you will use it directly from our drive. Okay, so guys, so now I will show you basically the correction of just this part. So, of course, let me know if you still have some problems to like access the driver. Okay, so the first image that you will see in this practical is this one. So as many of you has guessed, it represents basically the Eiffel Tower, right here. Then, as I said before, the idea is that you have to retrieve the latitude and longitude of the central pixel of this patch. So here, in the part of the code that was missing, you basically have to insert X and Y to correctly retrieve the longitude and latitude of the point. Once you have done that, what you can do to double check that is correct is basically to copy paste these two positions into Google Maps and check if it's actually correct or not. In our case, it is, no worries. And then what you have to do is basically to go back from the latitude and longitude to the pixel position of Sentinel-2 image. So in the missing part of the code, that was this one, you just have to insert these two values, X and Y, to finally retrieve the correct column and row in the Sentinel-2 patch. Now, at this point, you will just run this part of the code that is basically all the function that you need to plot the different spectral images. And here, what you have to insert is indeed the position in the image of the central pixel corresponding to the Bederto image. And what you will retrieve is something like this. So first, you will have the RGB image of the Sentinel-2 with more context. The context is decided here in high size, basically. And then you will also be able to see the corresponding image, but using different bands, and so also with different resolution, because we know that in Sentinel-2 there are the bands with different resolution. We discarded the bands with the resolution of 60 meters, but we have all the others. Okay, at this point, I didn't put it, but I know by. At this point, you have to retrieve also the elevation of the corresponding point of the latitude and longitude, because as we said, for SAR images, you also need the altitude due to the deformation, geometrical deformation present. So I guess there are also different API that you can use. Like I work with this one provided by IGN, but for sure there are also others. And using the elevation here, you will save the altitude of the corresponding points. In this case, 34 meters. Because it's not the point of the Eiffel Tower, but it's like an area very close to it. Then you will be able to take a look to the Sentinel-1 VV and VH channel. Again, the logic behind the code is very similar, so here you will have to put the two pixel location. And finally here, I hope you had the opportunity to travel a bit inside the dataset, but the idea is just that if you change the image index, you will be able to see different images and all the corresponding channels of the Sentinel-1 and Sentinel-2, like this, with the Sentinel-1 in RGB. And then finally here, if you just change the image value and the question and answer value, you will be able to have the information about different images. So all the image have an ID, and then all the question ID. So if, for instance, you, like, in this case, we are taking the first image and the first question and answer of the first image. So basically this one that corresponds to is a residential building present in the image. But of course, if you change it, you will have different question and answer. Okay, so I hope that you were able to travel a bit inside the dataset, but if you were not, you can do it at home. The data will stay there. So now I would move to the next part, which is about the model. So, what do I have to do? Okay. Okay. So for the architecture that we presented, the idea is indeed to use different modalities and different resolution inside a model. So we used a visual BERT. Basically, what we did is that we took the question, we tokenized it, then we extracted the feature from SAR, the multispectral data, and the very high resolution. For the SAR data and the multispectral images, we used pre-trained network on a classification task using big EarthNet indeed. While for the very high resolution, we used ResNet 152 pre-trained on ImageNet. Then we concatenated all the features and we inserted them in the in Visual BERT to have a prediction that, as Sylvain announced before, is treated as a classification problem. So basically, you have a list of possible answers, and then the most possible answer will be chosen. Afterward, we had an average and overall accuracy of 65, almost 66, and 55%. So in this case, when you treat a VQA problem as a classification problem and your answer is a single label, usually you use accuracies, so average and overall. Other models treat the problem also with multi-label classification, so in that case you have to use also other scores, but in this project it was a single label. Okay, so now we will move to the second practical, where the idea is that you will basically inference on the model and also on one of the ablation study that we have done. The ablation study that you will basically inference on is using only the very high resolution images, so only the BD-Ortho. So here we are. You have to do basically the same procedure as before. So mount the driver, install rastereo. You will also have to insert, as before, the SAR_display file. You will then install all the packages. So basically the same as before. Then you will have to load the stillbirth, and now you will have the model itself. So as I told you, the main idea is that you will tell the model if you are using only the very high resolution image or also the Sentinel-1 and the Sentinel-2. The model that we used is indeed VisualBird VQA. The number of labels, so the possible answer, are 1,000. And something that we do also after choosing how many answers we will have is that we check what is basically how many questions are the one that we are choosing covering. So in our case, we were covering almost 90% of the dataset. This means that the other answer, that the one that we discarded, were so little that it's a nice approximation, basically. And then, as I told you, for the BD-Ortho image, we used ResNet 152 using the weights of ImageNet, while for Sentinel-1, we used the weights that we pre-trained on a classification task, and of course, we keep trained the network during the training of the overall model. And similarly, for the Sentinel-2, you, of course, have all the weights in the drive. And yes, basically then you forward, but I guess you already know these parts. And you concatenate everything to then insert it here into VisualBird. So this part is already done. It's just to explain you a bit the model, and you just have to run it. Here we save all the split test images, question and answer that in theory you have a bit explored in the previous Jupyter notebook. We have the value for the normalization of the images. So for the BD-Ortho, the Sentinel-2, tac, tac, tac. And then we have all the different values that the model will use. So in this part, you will have to code just a very, very small part that is basically about the accuracy. So here and here. What I would suggest you is that maybe at the beginning, instead of using a ratio of 1, which means to use the overall dataset, to use a ratio of like 0.2, so take just a small part of the dataset to see if your code is working well. And then you will just have to test the two functions. So the first one with only BD-Ortho images. So we put true in the BD-Ortho and false for Sentinel-1 and Sentinel-2. And here you just have to choose like if it's multimodal or not. And same here, but using all the different modalities. So the model using only BD-Ortho is pretty fast, while the one that uses all the different modalities is slower, because basically we are creating the patches for Sentinel-2 and Sentinel-1 online, so while the model is training, so it's a bit slower. And for this reason, I've already saved and shared the PKL files here, so that you can create the confusion matrix without having to really run the models, because it may take time. I'm not sure you will be able to run it. It should take like 10 to 15 minutes. But if we don't have time, you can just use the confusion matrix, like the files that are already saved. And yeah, then you will have to plot the confusion matrix, but the idea is that I will give you again 10 minutes, I will walk, and then we will discuss the results. Okay, guys, so I will move to show you the solution for this part. So, okay, done, 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 done. Okay, so what you had to code here, basically for the calculation of the accuracy, so overall and average accuracy, was that you basically had to save all the prediction and all the ground truth, and then to calculate the overall accuracy, you had to do problem? No, okay. Okay, so basically you had to divide the summation of all the accuracy value with the summation of all the number of questions by category. Then here, like, I had to move above this part because yesterday I modified it, but yeah. And for the average, what you had to do was the summation of the category accuracies value divided by the len of all the category accuracies. So I'm not sure if you had time to test both models, but what you can see is that only using the Bedorto images, the accuracies were quite low. So we have an overall accuracy of almost 28% and an average of almost 15%. While using the multimodality, even if the model is slower, the overall accuracy is more than 66% and the average more than 77%. So we gained quite a lot in this case. Of course, then, like, this is just a small sample of the overall dataset. And yeah, then if you want, you can check basically question by question all the different accuracy if you want to see in which classes the use of multimodality was the most useful. What we have noticed from our results in the overall paper is that the multimodality is mostly useful when tackling with water bodies or in general with land cover questions. Or also, like, really in questions that needed more context. So, for example, to understand in which region we were in France, or which part of the city we were into, the flood types, yeah. Then, in this last part, what you had to do was basically write the code to compute the confusion matrix that are, as Sylvain said, very useful to understand basically the behavior of your results. And so you had here to insert that you wanted a confusion matrix that represented the answers and the predictions, so the ground truth and the prediction. And then you, if basically the size of the confusion matrix that you choose is of a certain size, you can also plot basically the name of the possible answer. And to do that, you have to check the selected answer, so basically the answer that we selected for the classification task. So here, the solution was selected answers. So what we can see from the confusion matrix of the Bede-Orto only model is that for yes and no questions, like we have kind of good results, meaning that even if the model is not correct, the possible answers are only those two. But we can see that, for example, for all the other questions, there is a bit of confusion. And then moving on the multimodality, we can much more clearly see that there is kind of a diagonal behavior. And so we are, the prediction are most of the time the answers. And okay, so now I will move to the last part. That will be very, very fast, no worries. And since we don't have much time, I will directly show you all the code. But I think it's very nice if then at home you try it. I mean, Quen is very popular and it can be very useful, so maybe it's also useful for your research in general. So once again, to make the Jupyter Notebook work, you have to mount the driver, install Quen, install Rasterio, and then you'll have, to import all the different packages, blah, blah, blah. Then you will save all the different JSON with question, answer, and images. And basically, what I've done in this part is that I have printed some questions that I liked. So I've chosen to use image 0, so the first image of our dataset, and then I've taken some index question, completely randomly, and then I've printed the question and answer. So some examples are, to which department does the area in this image belong to? The image was this one. Or is this area prone to floodings? What is the largest building in the image? What is the distance of the smallest building with respect to, and then a point in the image? So these are some examples of our dataset question and answer. And then what you can do is basically just to install Quen 2VL. And then you can basically iterate on the image and the questions that I have just showed you. So here you put the image, and here you put the question. You just inference on Quen 2VL, and then you have the outputs. For each image, so for each question and answer, it will take around 1 minute and 30 seconds to have the output. But what we can see in general is that the answer that this model gave us, that is a decoder-only model, so basically it will give us a long answer, not just a specific one as we have in our classification task. In some type of question, it's really working pretty well. So for instance, to which department does the area in the image belong to? We have a very, very long answer, but the answer is indeed correct. So it is able to correctly say where the image is from. Then, is the area prone to floodings? We have again a very long answer, so it's relatively flat, has a grid-like street pattern, blah, blah, blah. So it's circling a bit around the answer that we want. But in the end, it says that the flooding risk is very low. But what we can notice is, for instance, that when we ask questions about values, the answers are quite bad. So, sorry, the question was, what is the distance of the smallest building with respect to, and then 1 point in the image? So first of all, weird number, parentheses 59, and then, yeah. While in this type of answer, a normal, a model that treats the problem as a classification task is more able to answer correctly. So the correct answer should have been 137.86 meters. And once again, the answer that you have is this one. So I think like we can finish. I would really suggest you, if you want and if you have time, to like try a bit more the codes, and maybe the dataset may be useful for you, I don't know. But if you want to explore it more, and if you want to at home inference on the two models, and then I think it could be very useful for you also to use a bit Quen. It's, yeah, I mean, this type of model are getting more and more popular, so it's always useful to know how they work. And that's it for me. I would just conclude with this slide. So, thank you for your attention, and here is the QR code basically of the paper of this different practical work. And yeah, a big thanks of all my supervisor and Hisham Boussaid, that it's another PhD and worked a lot with me on this. Thank you.
Okay, Lucrezia, sorry. We have a question from the audience.
So I have a question. So if, as the professor also designing the model, that there is a like backbone type of encoder, and then there's the head of the either classification or possible of the regression, and probably also and so on and so on and so on of the head of the prediction itself. Is there any way that the model knows that in this particular question is actually a regression task, and then either not classification task, or is it like some typical a switcher in the middle between latent space to the predictor head that could be acquired to do multiple tasks?
I saw some models that have first a classification on the type of question. So basically, when you like the model receive the answer, there is first a classification on, okay, what is the type of this question? Is like area, is presence, is comparison, and if it's, for instance, area counting, then you do a regression. Otherwise, you do a classification.
Okay, so so then with the single backbone, it's possible to have multiple type of head,
yeah.
Just because we can able to convert the question into a latent space, basically.
Yeah, or you just like put everything inside and like
wish best.
Yeah.
Okay, thank you.
Any other question? If not, we can thank Lucrezia for the presentation.
Thank you.